In this video, we'll discuss some properties of determinants by seeing how they behave with respect to the various matrix operations. So the first property we'll look at is what happens to the determinant when we multiply two matrices together. And the statement is that the determinant of a product is the same as the product of the determinants. Right, so basically it means that if you multiply two matrices together and then calculate the determinant, is the same as calculating the determinant of the individual matrices and then multiplying the determinants together. So here I'm not going to really discuss in detail why this is true, because it would be fairly lengthy to write out. But the basic idea is that if in the case where the determinant is 0, right, so that would mean that either A or B would have, or both would have determinant 0, and when a matrix has determinant 0, that means it's singular, and so that means that either A or B would have to have a row of all zeros. And so if one of the two has a row of all zeros, then the product will also have a row of all zeros, and so the product would also have determinant 0. Right, so this is true in the case where the determinant is 0. When in the case where the determinant is non-zero, the idea there is to, so both of them would have non-zero determinant. So the idea there would be both matrices will then be non-singular, and so for non-singular matrices you can write them as the product of a bunch of elementary matrices, and so then you just have to look at how the determinant behaves in terms of products of elementary matrices. And so you want to look back at theorem 3.3 from the previous section on how the determinant works with elementary row operations and row matrices in elementary matrices. But in any case, let's go back to the statement of the theorem. Right, so again, it says that the determinant of the product is the same as the product of determinants. So the statement is written for two matrices A and B, but the property also carries through to longer products. Right, so if you're multiplying a bunch of matrices together and then taking the determinant, it's the same as, again, calculating the determinants individually and then multiplying them all together. Okay, so let's see this property in action by looking at this example here where we have two 2x2 matrices. So first let's calculate their individual determinants. Right, so what is the determinant of A? Right, so let's remember the 2x2 formula. So determinant of A, B, C, D is AD minus BC. There's A times D minus B times C. So the determinant of A would be 1 times 4 is 4 minus a negative 4. So that's 8. What is the determinant of B? 0 minus 6 is negative 6. So multiplying together, so determinant of A times the determinant of B gives me negative 48. Okay, so that's calculating the right side of this equation. Okay, so now let's look at the product A times B. So first let's multiply the two matrices together. So first we do the matrix multiplication. Okay, so what do I have? Negative 1 plus negative 6 is negative 7. 2 plus 0 is 2. Negative 2 plus 12 is 10. And 4 plus 0 is 4. And then now, again, I use the AD minus BC formula, right? So I get negative 28 minus 20, which is equal to negative 48. And so we see that they're the same, calculated both ways. Okay, so it doesn't matter which way you calculate the determinant of a product. Okay, so basically the determinant behaves in terms of matrix multiplication the way you expect it to. Okay, so let's look at the next property. So here we look at how the determinant behaves with the next operation we have, which is scalar multiplication. So this theorem basically says that if you first scalar multiply a matrix and then calculate the determinant, it's the same as calculating the determinant of the matrix by itself and then multiplying that constant to the nth power, right? So basically the reason is you don't just multiply by the constant, but you also have to take the constant to the nth power, is from property 3 in 0.3.3, it says that if you multiply a matrix by if you multiply a single row in a matrix by a constant, then the determinant changes by a factor of that constant. And so if you multiply that constant to all of the n rows of A, then the determinant changes by a factor of c to the n. Okay, so this is how the determinant works for scalar multiplication. So again, let's take a look at this property in action by looking at this small example here, right? So so let's first look at c times a. So c is negative 3. So negative 3 times the matrix. So I'm scalar multiplying. That means I multiply every entry by that constant. So this gives me negative 3, 6, then negative 6, then negative 12. And then now we calculate the determinant of this. Again, by using the AD minus BC formula. So what is this? This is 36 minus a negative 36. So that gives me 72. Okay, so now what is the determinant of A by itself? So again, AD minus BC, that's 4 minus a negative 4. 4 minus a negative 4. So that gives me 8. Because it's 4 plus 4. And okay, so what was my constant C? That was negative 3. Right, so here this is 2 by 2. Right, so n is 2. Right, so c to the n times the determinant of A, in this case would be negative 3 squared times the determinant of A, which is 8. Right, so that's 6 times 8. No, 9 times 8, right, because negative 3 squared is not positive 9, and then 9 times 8 is 72. Right, so again, we see that these two are the same. Okay, so that's the determinant when we're dealing with scalar multiplication. Okay, so now we're going to look at how the determinant behaves with the matrix inverse. So we have two separate statements here, but essentially you can take them together, right? So it says that a matrix A is invertible if and only if the determinant is non-zero. And also you can calculate the determinant of the inverse by 1 divided by the determinant of A. So the theorem 3.7, you can also turn around to say that the determinant of A is equal to 0 if and only if A is not invertible, right? So it's equivalent to, saying that is equivalent to the way 3.7 is stated. Okay, so it's not difficult to see why this has to be true, right? Because from the definition of inverse, right? So if A is invertible, then A inverse has to exist. And furthermore, we have the equation A inverse A is equal to the identity matrix, right? So the A inverse has to cancel A out. So again, this is just the definition of what it means to be invertible. But then, what does this mean in terms of the determinant, right? So we can take the determinant of both sides. And on the left is just the product of A inverse with A. But we already know from theorem 3.5 that the determinant of product is the product of the determinants. So determinant of, so let me write it using the vertical bars, right? So A inverse A is equal to 1, right? Because the determinant of the identity matrix is just 1, because the identity matrix has all 1s on the diagonal, and 1 times 1 times 1 is just 1. Okay, so now we get this equation involving the determinants. So the product of determinant of A inverse with the determinant of A has to be equal to 1. But now we can see that neither of these can be 0, right? Because if at least one of them were 0, then the product would be 0 and not 1. So this means that this and this are both not equal to 0, right? So both their determinants are not 0. And then if I solve this equation for this determinant, right, so I can just divide the determinant of A over to the right side. And I get exactly this equation here. Okay, so it's not too difficult to see why these statements are true. And again, usually the way we think about theorem 3.7 is that it gives us a condition to check when a matrix is not invertible, right? So if you can calculate that the determinant of a matrix is 0, then you know automatically that it cannot be invertible. Okay, so so putting this together with what we know about how a matrix is related to systems of linear equations, we have several equivalent conditions now, right? So again, this statement here, if you know that a matrix is invertible, then automatically the determinant is not equal to 0. But we've already discussed other things previously with respect to invertible matrices, right? So if you have a system of n equations in n variables, then you can write it as a matrix equation like this, and it's a simple matter of solving for x by multiplying on the left by A inverse, right? So x, let me write this in blue, right? So this is x. You can solve this by multiplying on the left by A inverse, right? So the unique solution would be exactly this, and then this equation has the trivial solution. This is the same situation, right? So x is equal to A inverse times 0, but then this is just equal to 0, right? So the only solution for this equation when A is invertible is the trivial solution. And then we also have the conditions that if A is invertible, then it's row equivalent to the identity matrix, right? So if you do the row reduced echelon form, of A and you get the identity matrix, then it's invertible. And and then finally, when A is invertible, then it can be written as the product of elementary matrices. Okay, so just from the fact that you can calculate, if you can calculate the determinant of matrix is non-zero, then you can deduce a lot of information about how the matrix behaves. So finally, we look at how the determinant behaves with respect to the matrix transpose. So basically, this theorem says that if you have a square matrix, then the determinant of A is the same, exactly the same as the determinant of A transpose. And this statement essentially boils down to the fact that the rows of A are exactly the columns of A transpose. And when we learned about cofactor expansion, we saw that it doesn't matter whether you do cofactor expansion along rows or along columns, right? So, and the first row of A is exactly the same as the first row of A transpose, right? So if you do cofactor expansion for the first row of A, it's essentially the same as cofactor expansion for the first column of A transpose, and so they're essentially the same. Okay, so let's again see this property in action, right? So for 2x2 matrices, you can just look at the formulas, right? So for 2x2 matrix, right? So the general formula for A is A. The general matrix for A is A, B, C, D, and the determinant of this is A, D minus B, C. What about A transpose? So I have to switch the rows and columns, right? So A, B, C, D going this way. And what is this? This is AD minus CB, but CB is the same as BC. Okay, so it's the same for 2x2 matrices. Okay, so let's look at this 3x3 matrix here. Right, so let's expand by first row. So I'm going to expand by first row. So if I write out what does it look like, right? So the pattern is plus minus plus, right? So you have 2 times the determinant of the submatrix, these 4 entries, and minus 0 times the determinant of this submatrix, so 1, 2, 3, 0, and then plus 1 times the determinant of this submatrix, so 1, negative 1, 3, 1. So what is this equal to? This is 2 times, and this is a 0. This is 0 minus 2, so that's negative 2, plus 1 times 1 minus the negative 3 is 4. So this negative 4 plus 4, which is 0. Okay, so the determinant of A is 0, expanding by first row. What about A transpose? A transpose looks like this. 2, 0, 1, 1, negative 1, 2, 3, 1, 0. And now if I calculate the determinant of A transpose, so I'm expanding by first column now. Right, so plus minus plus. Right, so what do I get? 2. And then the submatrix is these entries here, so negative 1, 1, 2, 0. And then this entry, so minus 0. Submatrix is 1, 3, 2, 0. Plus 1. Submatrix is 1, 3, negative 1, 1. And then I'm calculating, so 2 times 0 minus 2, negative 2. This is 0. And plus 1 times 1 minus the negative 3 is 4. So again, it's negative 4 plus 4, which is 0. And so we again see that this and this are the same. Okay, so the determinant is exactly, determinant of A is the same as determinant of A transpose. And then on the bottom of this page here, we introduce a concept called an orthogonal matrix, right? So what it means for a matrix to be orthogonal. So the condition for an orthogonal matrix is that A inverse is the same as A transpose. So we'll see later on that when we learn about inner products, and this is related to how the rows and columns, the individual rows and columns of the matrix behave. So the condition for orthogonality, it's actually easier to, instead of calculating A inverse and then calculating A transpose and then comparing the two, to check this condition, it's easier to check this calculation here, right? So if A transpose is the same as A inverse, then basically it means that if you multiply by A, if you multiply A by A transpose, they should cancel out, right? Because it's the inverse. A transpose is now the inverse, so they should cancel out and get the identity matrix. So so again, to check for orthogonality, it's easiest to just do the multiplication like this and then check if it's the identity matrix, right? So here I have two examples, matrices, 2 by 2 matrix and a 3 by 3 matrix. So the matrix A, right? So I set up the calculation A transpose times A, and you see that the resulting product is not the identity matrix, right? So that means that A is not orthogonal. However, for B, right? So again, I did the calculation here, B transpose times B. You see that you do get the identity matrix, so that means that B is orthogonal. So again, to check for orthogonality, it's typically easiest to check this equation here, and then if you get the identity matrix or not, that'll tell you whether it's orthogonal or not.